We want to continue in this video with real-world examples of the particle in the box and talk a little bit about electrical conduction and a bit more about tunneling. Electrical conduction, let's say for example we had two sodium atoms neighboring one another. We have the level 1 electrons, very little overlap if any. Level 2 electrons, very little overlap if any, but if we bring those atoms close enough together, the level 3 orbitals, the level 3 energy levels will overlap even in the forbidden region. So if we consider each sodium atom to be particle in a finite box, in the classically forbidden region we'll have some overlap on level 3. That significant overlap will allow electrons to jump easily from one atom to the next. It won't take much potential energy to start driving them across, say a voltage on one end and a voltage on the other. So the valence electrons become delocalized across the sodium atoms in an array of overlapping orbitals or wave functions. The electron orbitals then for a box of particles, similar to what we saw for conjugated systems, only much larger and with more potential particles. Let's think about that box as a macroscopic length. Let's say we have a whole centimeter of sodium atoms. We can think of it as a whole centimeter of sodium ions serving as the provider for the potential energy of each valence electron, but a whole centimeter of sodium atoms lined up end to end would be 2 times 10 to the 7th atoms, each of them kicking in one electron. So that means they're going to fill up 1 times 10 to the 7th energy levels in that box, if we think of it as a particle in the box. To calculate the energy level difference between the HOMO and LUMO then, we would have n plus 1, where n we just said is 1 times 10 to the 7th squared times h squared over 8ma squared, where a is going to be a centimeter or 10 to the minus 2 meters. M is still mass of an electron, and then n is going to be this number, or half of this number, and n plus 1 is going to be 1 plus half of this number. If we work that out and do the math and substitute in 1 times 10 to the 7th for n, we get a difference in energy of only 10 to the minus 26 joules. That's a very, very, very small difference in energy, considering that kT is much larger than that. So the amount of energy that's around just as a result of atomic motion at 300 Kelvin is much larger than this amount. And so at room temperature, it's very easy to promote an electron from one level to the next if we think of those electrons as being in a 1 centimeter box. Now in insulators like diamond or rubber, all the valence electrons orbitals that are very closely spaced are all filled with valence electrons, and so it becomes very difficult to promote one to the next level in the way that we did here. The next question comes up: what happens if we have an electron that has a very significant wave function in a particular low potential energy area? Let's say this is 0 potential energy, and then there is a barrier, an area of potential energy that's greater than 0 but not infinite, and then past that by some distance is another area of very low potential energy. Well, the electron can tunnel through and have a non-zero probability of being found over here. And how close to 0 is the probability of finding it over here? Well, that's related to how high the potential energy barrier is and how wide the space is that the electron would have to travel through, or what we call tunneling through, to get there. This becomes very, very important in applied chemistry and physics when we start to talking about scanning, tunneling microscopy. We have a sample that we're interested in that has an applied voltage to it, and then we have a metal tip that comes down here, very, very close, certainly within nanometers or picometers of the substrate. And we apply a voltage difference across here, and we can tell how far the very point, the very tip of our needle, if you will, is from the surface that we're scanning by the voltage, by the by the amperage, by the number of electrons that will pass through based on the voltage. Basically, we said that the probability of finding an electron tunneling across is going to be related to the potential difference, which we set by setting up our voltage, and the distance, which is what we're measuring or calculating by the measurement using scanning tunneling microscopy. So the tip and the surface each represent a box where the potential is essentially zero, more or less like we found in the sodium array. The space between them represents a finite non-zero potential energy barrier with a narrow enough, usually less than a nanometer, space that an electron can tunnel through if enough voltage is applied. The current is going to be inversely related to the decay of the wave function as the electron passes through the barrier, and that's going to be directly related to the distance from the tip to the sample. So a scan of a whole surface with the tip at constant height can give an atomic scale typological map of the surface. And so that's how scanning tunneling microscopy is done. The wave function amplitude decays in the barrier according to this equation. Wave function is equal to constant times e to the negative 2m, difference between energy and potential energy, over h squared, square rooted, and then all of that multiplied by x. So this is the function we've looked at before. So the tunneling current through a width of a barrier will be proportional to the square of that wave function, where x is the width of the barrier. So if the difference between the energy and the potential energy is 4.5 electron volts, how much larger would the current be for a barrier of with 0.2 nanometers than for 0.3 nanometers? And this is something I want you to try on your own based on these equations, and we will work these out together in class next time we meet. And then try these numbers out using the mass of a proton instead of the mass of an electron, and give us your thoughts on how promising the idea of inventing a proton tunneling microscope would be instead of an electron tunneling microscope. And again, we'll work on these together in class as we have time. Now, regardless of what we calculate on that problem, there are examples of hydrogen atoms tunneling in chemistry. For example, let's look at this reaction where a particular alcohol transfers its proton to a particular alkoxide ion, and we know that the transfer happens because R1 is in some way different from R2. If this reaction occurs via normal thermal activation, the rate should be the same if the reaction is done using a deuterium alcohol rather than a regular protium alcohol. However, this reaction occurs much, much slower for deuterium alcohols than it does for protium alcohols because tunneling rate depends on decay length, which depends on the square root of mass. And so since deuterium is twice as heavy, if the hydrogen is tunneling in these cases, it's going to happen 1.4 or square root of 2 times slower as a result. In the next video, I want to take a few minutes. The next video will probably be fairly short and will be material that's not covered in the book and won't be covered directly on the test, but just to give an illustration of an example of tunneling that has been published regarding even heavier atoms than hydrogen or deuterium.